Alright, fellow dreamweavers, cosmic prospectors, and seekers of the comfortably absurd, welcome. Settle in. Let the weight of your day, with all its petty squabbles over parking spaces and lukewarm coffee, just dissolve. We're trading those fleeting frustrations for something altogether grander, and, if we're being honest, far more bafflingly pointless in the grand scheme of things. Tonight, we embark on a rather peculiar treasure hunt. Not for chests of gold buried beneath some forgotten X. Oh no. We're going galactic. We're going expensive. Impossibly, comically, terrifyingly expensive. We're venturing into the shimmering, silent vaults of the cosmos to whisper about the universe's trillion-dollar treasures. Materials so rare, so potent, so mind-bendingly difficult to acquire that putting a price tag on them feels like trying to bottle a supernova with a thimble. It's a journey into cosmic riches, yes, but let's be clear from the outset. This isn't about filling your celestial bank account. Most of these treasures would kill you long before you could cash them in. Or, perhaps more amusingly, the universe simply doesn't care for your currency. It operates on a different kind of exchange rate, one involving fundamental forces and eons of time, not little green pieces of paper or blinking numbers on a screen. So, as you drift, as your breath deepens and your muscles soften, imagine yourself wrapped in the velvet cloak of interstellar night. All around you, the stars aren't just twinkling lights. They are distant forges, galactic refineries, churning out wonders and horrors with a majestic indifference that can be, paradoxically, quite soothing. You see, our human concept of value is a rather quaint, terrestrial affair. It's based on scarcity, desire, utility within our very specific, rather fragile biosphere. But out here, in the grand, echoing silence of the cosmos, value takes on new and often darkly amusing dimensions. What makes something priceless in the universe? Sometimes, it's the sheer, almost vindictive difficulty of its creation. The universe cooks up some substances under conditions so extreme, temperatures so high, pressures so immense, that our most advanced laboratories look like a child's chemistry set by comparison. To replicate these processes, to even snatch a microscopic sample would cost, well, let's just say your planetary GDP wouldn't cover the down payment. Makes that artisanal loaf of bread seem like a bargain, doesn't it? Other times, the value lies in a material's revolutionary potential. Imagine holding something that could rewrite physics, unlock limitless clean energy, or perhaps, just perhaps, confirm that we are not, in fact, the only sentient beings in this vast expanse foolish enough to ponder the price of stardust. Such a discovery wouldn't just be valuable, it would be shattering, transformative, possibly even a little bit terrifying. What if the answers we find aren't the ones we were hoping for? The universe, bless its cold, indifferent heart, rarely checks if we're ready for the truth. And then there's value born of absolute rarity. Things that exist in such vanishingly small quantities, or in places so utterly inaccessible, that to possess even an atom would be a scientific triumph akin to understanding why socks go missing in the laundry, a truly profound mystery. So, as we begin our sleepy quest for these cosmic fortunes, let go of the idea of tangible wealth. We are prospectors of the mind, sifting through nebulae of thought, mining asteroids of imagination. The gold we seek is understanding, the diamonds are moments of awe, and the platinum is perhaps the wry smile that comes from realizing just how wonderfully, terrifyingly out of our depth we truly are. Picture the cosmos not as a static backdrop, but as a dynamic, ever-changing entity. It's a place of breathtaking beauty, yes, swirling galaxies like divine brushstrokes, nebulae blooming like impossible flowers in a garden of infinite night. But it's also a place of stark, unyielding realities. Extreme temperatures that would flash freeze or instantly vaporize you. Radiation that would unravel your very essence. Pressures that would crush you into a subatomic smear. And distances so vast, so mind-numbingly empty, that the concept of loneliness achieves a new, almost artistic perfection. Makes that slightly awkward family dinner seem like a bustling social gala, doesn't it? Our journey tonight will gently touch upon these treasures. We'll start with things that almost feel attainable in a highly theoretical, wildly optimistic sort of way. Then we'll drift further out into realms of matter so exotic, so potent, that they blur the line between science and sorcery. We'll talk about elements rare on Earth but perhaps strewn across the moon or lurking in the hearts of gas giants. We'll marvel at diamonds born from celestial violence and ponder the bizarre nuclear pasta cooked up in the cores of dead stars, a cosmic dish probably best left untasted. We'll even dare to whisper about the alchemical dream of stable superheavy elements, and finally the ultimate prize, the most expensive substance ever conceived, antimatter. But through it all, remember the gentle irony. We, tiny fleeting beings on a pale blue dot, presuming to assign value to the building blocks of the universe itself. It's a bit like an ant declaring a skyscraper expensive. The skyscraper, much like the universe, simply is. It doesn't much care for the ant's economic theories. So let these whispers of cosmic fortunes be a lullaby. Let the sheer scale, the unimaginable energies, the profound mysteries, and yes, even the stark, unromantic truths wash over you. There's a strange comfort in our insignificance when viewed against such a backdrop. Our daily worries, our anxieties, they shrink, don't they? They become like tiny dust motes dancing in a sunbeam, visible for a moment, then gone. Allow your mind to drift, to wander through these star-dusted vaults. Don't try to grasp it all, don't try to calculate. Just be. Be present in this shared dream of cosmic riches, where the greatest treasure is perhaps this moment of peace, this quiet contemplation, this gentle slide towards sleep, wrapped in the vast, indifferent, and yet utterly magnificent embrace of the universe. The door to the vault is creaking open. Let's drift inside. And so we drift, leaving behind the earthly clamor, the terrestrial hustle. Our first port of call on this sleepy treasure hunt is a familiar celestial neighbor, one that has graced our night skies and inspired poets and dreamers for millennia, the moon. She hangs there, a serene silver disk, seemingly barren, cold, and perhaps a little underwhelming compared to the fiery drama of distant nebulae. But hold that thought. Hidden within her dusty regolith, and whispered about in the halls of science, is our first treasure, Helium-3. Now, Helium-3 isn't the kind of treasure that glitters. You can't wear it around your neck or display it in a velvet-lined case. It's a gas, an isotope of helium, which means it's a slightly different version of the stuff that makes balloons float and your voice sound hilariously squeaky. Specifically, Helium-3 has 2 protons but only 1 neutron in its nucleus, unlike the common Helium-4 which has 2 of each. A subtle difference, you might think. Like choosing between regular and decaf, perhaps. But in the world of physics, that one missing neutron makes all the difference. It's the secret ingredient, the whisper of potential that makes Helium-3 so alluring. Imagine for a moment breathing in the air on the moon. Well, you can't, of course. There isn't any, not in the way we understand it. It's a vacuum, a profound silence broken only by the crackle of your own suit's radio, assuming you had one. But embedded in the very soil, the top few meters of lunar dust accumulated over billions of years, is this Helium-3. It's a gift from the sun, a constant stream of particles known as the solar wind, which has relentlessly showered the moon's unprotected surface. Earth, with its robust magnetic field and thick atmosphere, deflects most of this solar largesse. We're rather good at self-preservation most of the time. The moon, however, naked and exposed, has been patiently collecting it like a cosmic piggy bank. Why is this particular gas so coveted? Its promise lies in nuclear fusion. Not the messy, complicated, and rather grumpy fusion we're currently wrestling with in giant, earthbound machines, trying to replicate the sun's core. Helium-3 offers a cleaner, more elegant path. When fused with deuterium, an isotope of hydrogen, the reaction produces normal helium and a proton. Crucially, it doesn't produce a shower of high-energy neutrons like many other fusion reactions. those neutrons are a problem. They make reactor components radioactive, requiring heavy shielding and creating long-lived waste. It's like a barbecue that leaves your grill glowing faintly for 1,000 years. Not ideal. Helium-3 fusion, however, is comparatively anitronic, fewer nasty neutrons. This means potentially safer reactors, less radioactive waste, and a more direct conversion of energy. It's the dream of clean, almost limitless power. Imagine a future fueled not by dwindling fossil reserves or complex fission, but by a gentle power source, its primary fuel scooped from the tranquil silver plains of our closest celestial companion. A beautiful thought, isn't it? Like harnessing moonlight itself. On Earth, helium-3 is incredibly rare. Most of the helium we find trapped underground is helium-4, the byproduct of radioactive decay. You might find a few kilograms of helium-3 as a byproduct of nuclear weapons maintenance, which, let's be honest, is not exactly a sustainable or particularly cheerful source. The entire atmospheric content is estimated to be mere tons. It's rarer than gold, rarer than platinum, almost a whisper in the elemental choir. But on the moon, the moon. Estimates suggest there could be over 1 million metric tons of helium-3 lightly peppered across its surface, particularly in the titanium-rich soils of certain regions. 1 million tons. That may not sound like much when you're talking about mining, but consider this. It's estimated that just 25 tons of helium-3 could power the entire United States for a year. Suddenly, that dusty, silent landscape starts to look a little more valuable. It's not glittering, but it has a quiet hum of potential, a serene promise. So, picture yourself drifting over the sea of tranquility. The Earth hangs in the black sky like a luminous blue marble, a vibrant jewel against the velvet void. Below you, the gray plains stretch out, cratered and ancient. It's a desolate beauty, a landscape of stark contrasts, light and shadow. And scattered within that dust, invisible to your eye, is this subtle treasure, this fuel for a gentler future. It's a lovely dream, isn't it? Lunar bases, gleaming fusion reactors softly humming, providing clean energy for generations. Spaceships ferrying this precious, invisible cargo back to a grateful Earth. It's a vision of harmonious expansion, of humanity reaching out, not just to explore, but to gather the subtle gifts the cosmos has laid at our doorstep. This is the serene promise of helium-3. It's not about instant riches, not about cosmic bling. It's about a quiet revolution, a potential shift in how we power our world, all locked away in the silent, sun-baked dust of our moon. It's a treasure that whispers of sustainability, of technological elegance, of dreams powered by starlight indirectly. It's the kind of value that doesn't shout. It hums, a low, resonant frequency of hope. But as with all treasures, especially cosmic ones, there's always a but. A little asterisk. A fine print that the universe, in its infinite wisdom and occasional penchant for dark humor, tends to write in invisible ink. The dream is beautiful, the science is tantalizing. But acquiring this lunar dream, well, that's where the gentle hum meets the cold, hard vacuum of reality. And that, my sleepy friend, is a slightly different story for a slightly later breath. For now, just bask in the gentle glow of that lunar potential, that clean energy dream, sleeping silently under a sky full of distant, uncaring stars. We were just basking, weren't we, in the serene potential of helium-3, that gentle power source sleeping on the moon. 1 million tons of it just waiting to fuel our utopian futures. Sounds rather straightforward, doesn't it? Like popping down to the cosmic corner store for a tank of future fuel. Except the universe, bless its stony heart, rarely makes things easy. Or cheap. Especially when it involves leaving our rather comfortable gravity well. So, let's gently, very gently, pull back the shimmering curtain of that lunar dream and peek at the logistics. The rather stark, silent, and monumentally expensive realities of actually getting our hands on this coveted gas. Because while helium-3 may be free for the taking on the moon, The taking part is where the cosmic bill comes due, and it's an itemized invoice that would make a billionaire weep. First you have to get there. Not just a quick Apollo-style jaunt for flags and footprints, mind you. We're talking about establishing a sustained mining operation. This means lunar bases, habitats, power generation. Ironically, you'll need a lot of power to get the power, life support, and all the associated paraphernalia to keep a bunch of highly skilled, probably rather grumpy space miners alive on an airless, irradiated rock. The initial investment for such an outpost? Think in terms of national budgets, plural. Perhaps the GDP of a reasonably sized country just to turn the lights on. Suddenly that free gas is starting to look a little pricey. Then there's the mining itself. Helium-3 isn't conveniently pooled in subterranean lakes, waiting to be tapped like oil. Oh no, that would be far too simple. It's sparsely distributed within the top few meters of lunar regolith, that fine, abrasive, electrostatically clingy dust that gets into everything. Imagine trying to extract a single specific grain of sugar from several tons of flour, using a very, very expensive vacuum cleaner in a spacesuit. To get a significant amount of helium-3, you need to process vast quantities of this regolith. Estimates suggest you'd need to heat hundreds of tons of lunar soil to around 600 degrees Celsius or more to release just 1 gram of helium-3. 1 gram. Think about the machinery required. Giant strip mining rovers, solar-powered heating plants, collection facilities, all designed to operate flawlessly in a vacuum, enduring extreme temperature swings from scorching lunar day to cryogenic lunar night, all while being bombarded by micrometeorites and solar radiation. These aren't your granddad's bulldozers. These are multi-billion-dollar, custom-built, high-maintenance marvels of engineering. And you'll need a fleet of them. The repair bills alone would be astronomical, quite literally. Who do you call for lunar roadside assistance? Probably another astronaut with a very expensive wrench and an even more expensive travel claim. And after you've scooped, heated, and collected, you then have to separate the helium-3 from the other gases released. Mostly hydrogen, helium-4, nitrogen, and some other trace elements. This requires sophisticated cryogenics and filtration systems, all adding to the weight, complexity, and, you guessed it, the cost. It's like panning for gold, except the gold is an invisible gas, the riverbed is the entire lunar surface, and your pan costs more than a small aircraft carrier. Let's talk scale. To get those 25 tons of helium-3 needed to power the US for a year, you'd need to process roughly 1.25 billion tons of regolith. That's digging up and cooking a patch of the moon roughly 20 square kilometers in area to a depth of 3 meters. Imagine a mining operation that vast, run by remote control or by astronauts whose overtime pay would probably bankrupt a small nation. The sheer energy required for this heating process is immense. Even using solar power, which is plentiful on the moon, when the sun is shining on your bit anyway, the infrastructure for solar arrays would be colossal. And once you've got your precious, hard-won helium-3 liquefied and stored in cryogenic tanks, you then have to launch it off the moon and send it back to Earth. Launching mass from a celestial body, even one with lower gravity like the moon, still requires a significant amount of energy and, therefore, fuel. It's the universe's cruel joke. You spend a fortune mining fuel only to burn a good chunk of potential profit just to send it home. It's like delivering a pizza that eats half of itself on the way. The estimated price tag? Some analyses in the early 2000s put the cost of producing lunar helium-3 at figures that would make it economically competitive only if terrestrial energy prices soared to unimaginable heights, or if the technology for fusion reactors using it became vastly more efficient and cheaper than anything we can currently envision. We're talking billions of dollars per kilogram, potentially. So, while its potential energy value is enormous, the cost to realize that potential is, for now, equally enormous, if not more so. It's a classic cosmic catch-22. A treasure locked in a vault that costs more to open than the treasure is currently worth on the open market. It's a stark reminder, isn't it? The universe offers these incredible bounties, these whispers of unimaginable power and progress. But it rarely offers them on a silver platter. There's always a catch, a challenge, a harsh reality check. The moon, so serene and beautiful in our night sky, is also a harsh, unforgiving environment. Its silence isn't just peaceful, it's the silence of an airless void. Its dust isn't just ancient, it's abrasive and problematic. Its treasures are not easily won. So, as you drift, consider this quiet, lunar struggle. The magnificent dream of clean energy juxtaposed with the gritty, monumentally expensive reality of space mining. It's not to say it's impossible. Human ingenuity, when sufficiently motivated or desperate, is a powerful force. But it does put our earthly endeavors into a certain perspective, doesn't it? Suddenly, that leaky faucet doesn't seem like such an insurmountable engineering challenge. The moon holds its secrets and its helium-3 with a cold, dusty, and very expensive grip. The dream of gentle power remains, but it's a dream that will require not just scientific breakthroughs, but an economic and logistical effort of truly lunar proportions. For now, perhaps it's best to just appreciate the moon for its ethereal beauty, a silent guardian of a potential that remains for the moment just out of practical reach. A pricey silence indeed. Leaving the moon and its pricey, silent promises of helium-3 behind, we let our cosmic current carry us further afield, into the vast, dark ocean between the planets. Our senses, real or imagined, tingle with anticipation, for out here, drifting in the lonely expanse, are different kinds of treasures. Not gaseous and invisible, but solid, tangible, and glittering with a more traditional allure. We're approaching the asteroid belt and beyond, seeking out those celestial wanderers, the leftovers from the solar system's formation, asteroids. And on some of these rocky remnants, legend and spectrographic analysis tell us, lie hordes of precious metals. We're talking about platinum piñatas in the void. Imagine, if you will, a giant, irregular rock tumbling silently through space. It's not particularly beautiful in the classical sense. It's pockmarked, cratered, perhaps a dull, grayish-brown. It looks like a cosmic potato, a rather uninspiring celestial clod. But looks can be deceiving, especially out here. For within this unassuming space rock could lie concentrations of platinum group metals, platinum itself, iridium, osmium, palladium, ruthenium, rhodium, that would make a terrestrial mining baron weep with envy. These aren't just any metals. On Earth, they are exceedingly rare and therefore exceedingly valuable. They are crucial for a myriad of industrial applications, from catalytic converters in your car, helping to clean the air, a rather noble pursuit for such shiny stuff, to sensitive electronics, medical devices, and of course jewelry that costs more than your annual salary. Their rarity on Earth's surface is partly due to their density. When our planet was a molten ball of goo, these heavy elements mostly sank to the core, well out of our reach. It's like all the chocolate chips sinking to the bottom of the cosmic cake batter. Terribly inconvenient. Asteroids, however, particularly certain types known as M-type, metallic, asteroids, are believed to be the shattered cores of ancient protoplanets, worlds that tried to form but were smashed apart by gravitational tussles or colossal impacts in the chaotic youth of our solar system. These metallic cores, never having undergone the same degree of planetary differentiation that sequestered heavy metals deep within larger bodies like Earth, could be incredibly rich in these elements. They are, in essence, flying chunks of what would be a planet's inaccessible heart. So, picture one of these M-type asteroids. It might be a few kilometers across, or perhaps just a few hundred meters. Spectrographs from Earth-based telescopes and visiting space probes hint at its composition. They detect the signature of iron, nickel, and tantalizingly significant percentages of these platinum group metals. One modest-sized metallic asteroid, say a kilometer in diameter, could contain more platinum group metals than have ever been mined in human history. Let that sink in. An entire history of terrestrial digging, toil, and environmental impact, all potentially dwarfed by a single, unassuming rock drifting between Mars and Jupiter. It's the stuff of science fiction dreams, isn't it? Gold rushes in space. Hardy asteroid miners and rugged spaceships, equipped with lasers and magnetic grappling hooks, staking their claims on these cosmic treasure chests. Fortunes made overnight, or rather, over several years of incredibly dangerous and complex space travel. The allure is undeniable. It's like finding a mountain made of solid gold, except this mountain is tumbling through the vacuum hundreds of millions of kilometers away, and doesn't have a convenient gift shop at the base. The dream is of flying gold mines, as you put it, or perhaps more accurately, flying catalytic converter component mines, which doesn't have quite the same romantic ring to it, but is probably closer to the truth of their industrial value. The idea is that if we could just reach these asteroids, tow them into a convenient orbit, or set up automated mining refineries on their surfaces, we could unlock a virtually inexhaustible supply of these critical resources. Imagine the implications. No more scrambling for dwindling terrestrial reserves. Prices for these vital materials could plummet, making advanced technologies more accessible, perhaps even enabling new ones we haven't yet conceived. It's a vision of post-scarcity, at least for these specific elements. A future where your catalytic converter is not a significant portion of your car's cost, and scientists have all the iridium they need for their experiments. They use it for some surprisingly mundane things, like high-durability spark plugs and crucibles for growing crystals, alongside more exotic applications. The fantasy is potent. You drift towards one of these metallic behemoths. Its surface, reflecting the distant sunlight, has a faint, telltale sheen. Your ship's sensors confirm it. Rich veins of platinum, palladium, rhodium, interwoven with common iron and nickel. It's a cosmic piñata just waiting for the right, multi-billion-dollar, incredibly sophisticated stick to crack it open and release the goodies. The universe, in its messy, chaotic formation, has inadvertently created these concentrated pockets of wealth. It's like it swept all the valuable dust bunnies into convenient, albeit very remote, corners. And we, with our ever-expanding technological reach and our insatiable appetite for shiny things, are looking up at these distant dust bunnies with a gleam in our collective eye. It's a seductive vision, this idea of plucking riches from the sky, of tapping into a source of wealth that dwarfs anything on Earth. The dream of getting rich from the cosmos, not through some abstract energy potential like helium-3, but good old-fashioned, solid, weighable, meltable metal. The kind of stuff you can stub your toe on, if you're not careful in zero gravity. But as with all cosmic treasures, this glittering dream has its own set of rather sharp, unyielding edges. The romance of the asteroid gold rush, like all gold rushes, tends to gloss over the dirt, the danger, and the distinctly unglamorous realities of the actual work involved. The universe might offer up these platinum piñatas, but it doesn't provide the napkins or the cleanup crew. And cracking them open? That too is a story laced with a healthy dose of cosmic buzzkill. For now, though, let the vision linger. Silent, metallic behemoths, laden with treasure, waiting patiently in the dark. A billionaire's dream, floating in the endless night. We were just admiring those glittering platinum piñatas, weren't we? Those M-type asteroids, laden with more precious metals than all of Earth's mines combined. A tantalizing prospect. The stuff of spacefaring entrepreneurial dreams. But now let's gently drift closer past the shimmering idealized brochures of asteroid mining and get a whiff of the cosmic grit. Because hunting these treasures isn't quite like a leisurely Sunday drive to the intergalactic mall. It's more like trying to wrestle a greasy, hyperactive badger in a zero-gravity tumble dryer, while simultaneously doing advanced calculus to avoid becoming a permanent, very lonely satellite of said badger. First, finding the right asteroid. The asteroid belt alone contains millions of objects, ranging from pebbles to dwarf planets. Most are just boring old rocks, S-types, stony, or C-types, carbonaceous, which are fascinating for science, sure, but not going to make you rich in platinum. Identifying a promising M-type requires careful, long-range observation, spectrographic analysis, and perhaps even sending out robotic prospector probes. This isn't like spotting a shiny nugget in a stream. This is sifting through a solar system's worth of rubble, much of it uncatalogued and potentially on an orbit that intersects inconveniently with your very expensive spacecraft. Miscalculate, and your multi-billion-dollar mining venture becomes a rather spectacular, albeit brief, meteor shower. Not the kind of quarterly report you want to deliver to your investors. Then, assuming you've found your metallic prize, you have to get to it. We're talking journeys of months, often years, through the harsh environment of interplanetary space. Constant vigilance against radiation, micrometeoroid impacts, equipment malfunctions. It's not a pleasure cruise. Your crew, if you have one, will be living in cramped quarters, breathing recycled air, and probably getting thoroughly sick of each other's company. The psychological toll alone would be immense. Imagine the HR complaints on a multi-year asteroid mining mission. Glargan keeps using my designated protein paste dispenser. The universe is vast, but human pettiness, one suspects, is infinite. Once you arrive, you're faced with a spinning, irregular chunk of rock and metal, possibly with no stable up or down. How do you even land on it, or more likely, dock with it? Many asteroids are loose conglomerations of rubble, barely held together by their own feeble gravity. Try to drill into one too aggressively, and it might just disintegrate into a cloud of smaller, equally problematic rocks. It's like trying to nail jelly to a wall, if the jelly was also trying to kill you with shrapnel. Let's say you manage to anchor your mining equipment. What then? Do you try to chew off chunks and process them on site? This means complex, automated machinery, robotic excavators, crushers, smelters, all operating in a vacuum with extreme temperature fluctuations, far from the nearest Home Depot for spare parts. The dust, a finer, more abrasive version of lunar regolith, will get into everything, abrading seals, clogging mechanisms. And what about power? Solar panels are an option, but their efficiency drops as you get further from the sun. Small nuclear reactors are another, but they come with their own set of safety and logistical headaches. You can't just plug into the celestial grid. Alternatively, you could try to bag the entire asteroid, if it's small enough, and tow it somewhere more convenient like lunar orbit or even Earth orbit. This is the big catch fantasy. But imagine trying to nudge a multi-million-ton rock through space. It requires immense, sustained thrust over long periods. Ion engines are efficient but slow. Nuclear thermal rockets are faster but more complex. And any miscalculation in your trajectory could turn your precious metal resource into an extinction-level event for some unsuspecting planet. Talk about high stakes. Oops, sorry Earth, didn't mean to drop that $1 trillion worth of platinum on your head. My bad. And then there's the economics, the cold, hard, and often deeply depressing numbers. The initial investment in spacecraft, equipment, personnel, and years of research and development would be staggering. Billions certainly, perhaps trillions for a fully fledged operation. To make that back, you'd need to extract and return truly colossal amounts of precious metals. And what happens to the market price of platinum if you suddenly flood Earth with thousands of tons of it? The very act of succeeding could devalue your prize. It's the ultimate ironic twist. You spend a fortune to get something valuable, and in doing so, make it less valuable. The universe has a cruel sense of humor when it comes to supply and demand. So, the dream of flying gold mines starts to look a little less like a shiny, straightforward venture and a lot more like a grimy, dangerous, economically precarious gamble. It's a cosmic lottery where the jackpot is immense, but the odds are long, and the cost of a ticket could bankrupt nations. The image of the rugged asteroid miner, sleeves rolled up, wrestling riches from the void, is a romantic one. The reality is more likely to be a team of highly stressed engineers in a remote operations center on Earth, staring at data screens, hoping a robot arm millions of miles away doesn't accidentally sever its own power cable. This isn't to say it's impossible or that it won't happen. Humanity has a remarkable track record of doing incredibly difficult and seemingly irrational things in pursuit of resources or knowledge. But it's important to peel away the romantic veneer and see the stark, complex, and frankly rather terrifying reality beneath. The universe offers these treasures, yes, but it guards them with layers of physical barriers, economic challenges, and a healthy dose of sheer, unadulterated danger. Getting your hands on that stardust, that cosmic platinum, means getting your metaphorical hands very, very dirty, and possibly irradiated, and quite possibly bankrupted. It's a sobering thought, isn't it? As you drift, let that grimy reality settle. The glitter is there, but it's coated in a thick layer of cosmic dust and fiscal uncertainty. Makes that terrestrial 9-to-5 grind seem almost relaxing by comparison. Having wrestled with the gritty realities of asteroid mining, let's allow our cosmic current to cleanse our imaginations, to carry us towards something with a more classic, undeniable sparkle. We're seeking out the universe's own brand of bling, the ultimate symbols of endurance and beauty forged in the most extreme conditions imaginable. We're talking about diamonds, my sleepy friends. Not the kind dug from the earth, born of mere planetary pressures, but diamonds from chaos, celestial gemstones formed in the heart of dying stars, in the shockwaves of asteroid impacts, or perhaps even raining down through the crushing atmospheres of gas giants. Diamonds, as you know, are simply carbon atoms arranged in a very specific, very strong crystal lattice. On Earth, this transformation requires immense pressure and high temperatures, typically found deep within the planet's mantle, hundreds of kilometers beneath our feet. These earthly diamonds are then brought closer to the surface by ancient volcanic eruptions, a rather violent delivery service for such elegant jewels. They are symbols of love, of wealth, of permanence. But the universe, in its inimitable style, has ways of making diamonds that dwarf our terrestrial processes in both scale and drama. Imagine for a moment a white dwarf star. This is the collapsed core of a sun-like star that has exhausted its nuclear fuel. It's incredibly dense, a sphere perhaps the size of Earth but containing the mass of our sun. And some of these white dwarfs, particularly those rich in carbon, are thought to eventually crystallize as they cool over billions of years. The entire core, a colossal mass of carbon, slowly transforming under unimaginable pressure into a gigantic diamond. Astronomers have found evidence for such a star, named BPM 37093, nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds. This celestial diamond is estimated to be about 4,000 kilometers in diameter and weigh in at 10 billion trillion carats. To put that in perspective, the largest diamond ever found on Earth, the Cullinan diamond, was a mere 3,106 carats before cutting. Lucy is rather more substantial. You wouldn't be wearing Lucy on your finger, you'd be orbiting it. The value of such an object is, of course, laughably irrelevant. It's a star-sized diamond. What more is there to say? It makes Earth's entire diamond reserve look like a pinch of glitter dropped on a cosmic beach. Then there are diamonds forged in violence. When a large carbon-rich asteroid strikes a planet, the colossal pressures and temperatures generated in the impact can instantly transform carbon in the asteroid, or even in the target rock, into diamond. These aren't your flawless jewelry-grade solitaires, mind you. These are often tiny nanodiamonds, or a unique hexagonal form of diamond called lensdaleite, which some theories suggest could be even harder than conventional diamonds. These impact diamonds are scattered across impact craters on Earth and have even been found in meteorites, tiny, glittering messengers from ancient cosmic collisions. Imagine holding a meteorite, a humble space rock, and knowing that embedded within it are microscopic diamonds, born in a flash of cataclysmic energy millions or billions of years ago. It's a piece of chaos you can hold in your hand, a testament to the universe's ability to create beauty from destruction. And the universe doesn't stop there. Let's drift towards the gas giants, planets like Jupiter and Saturn, or even Uranus and Neptune. Their atmospheres are rich in methane, which is a molecule made of carbon and hydrogen, CH4. Deep within these colossal planets, the atmospheric pressure becomes truly immense, millions of times greater than Earth's sea level pressure. The temperatures too soar to thousands of degrees. Under these extreme conditions, scientists theorize that methane molecules are crushed, the carbon atoms breaking free and squeezing together to form, you guessed it, diamonds. These diamonds, perhaps initially like soot, would then precipitate, forming diamond hailstones, or even diamond rain, sinking deeper into the planet's atmosphere due to their density. Imagine vast, glittering showers of diamonds falling through turbulent hydrogen-helium clouds, eventually perhaps forming a liquid diamond ocean or even a solid diamond layer deep within these giant worlds. It's a breathtaking, almost surreal image. A planet where it literally rains riches. Though, of course, riches that are utterly inaccessible, buried under thousands of kilometers of crushing atmosphere. Not exactly a place for a leisurely stroll with a diamond-collecting umbrella. These cosmically formed diamonds, whether the star-sized heart of a white dwarf, the microscopic shrapnel of an impact, or the theoretical diamond rain on a gas giant, speak to the universe's raw power and its surprising artistry. Carbon, one of the most fundamental building blocks of life as we know it, can also, under the right or wrong, depending on your perspective, conditions, become one of the hardest and most aesthetically prized substances in the cosmos. There's a certain poetry to it, isn't there? The same element that forms the soft graphite in your pencil, that forms the basis of our organic bodies, can also create these incredibly resilient, sparkling gems. It's a reminder of the transformative power inherent in the universe, the way simple ingredients can be alchemized into extraordinary forms by the brute force of physics. So, as you float in this calm, dark space, picture these celestial bling factories. A cooling star, slowly crystallizing into a diamond of unimaginable proportions. The fiery flash of an asteroid impact, seeding a barren landscape with microscopic, super-hard gems. The surreal, silent fall of diamond rain through the crushing depths of a gas giant's atmosphere. These aren't treasures you can mine or sell in the conventional sense. Their value lies in their testament to the extreme forces at play in the cosmos, and the unexpected beauty that can arise from them. They are nature's ultimate sculptures, forged in crucibles far grander than any earthly workshop. Sparkling reminders of the universe's enduring, chaotic, and occasionally very glamorous creativity. We were just marveling at the universe's capacity for creating diamonds, those sparkling symbols of endurance, weren't we? From star-sized crystals to microscopic impact shards. And we touched upon the rather poetic, if somewhat terrifying notion of diamond rain on gas giants like Jupiter, Saturn, Uranus, and Neptune. It's a beautiful image, glittering showers falling through alien skies. But let's linger here for a moment in the swirling, crushing atmospheres of these colossal worlds, and really feel what that diamond rain implies. Because while it sounds like a jeweler's fantasy, the reality is a stark reminder that cosmic beauty often comes hand in hand with conditions that are, to put it mildly, uninviting. In fact, they're downright lethal. Imagine yourself not as a detached observer, but somehow, impossibly, present within the upper atmosphere of Neptune, one of our ice giants. You're not really falling in the traditional sense, but being buffeted by winds that can reach over 2,000 kilometers per hour, the fastest in the solar system. Supersonic gales of hydrogen, helium, and methane. The temperature at this cloud top level is a brisk minus 200 degrees Celsius or colder. Your spacesuit, assuming you had one capable of even beginning to withstand this, would be creaking under the strain before you even got to the interesting part. Now let's descend. Deeper and deeper into this frigid, turbulent atmosphere. The pressure mounts relentlessly. From one Earth atmosphere at the surface, defined as the point where pressure is 1 bar, it rapidly increases. Thousands of atmospheres, tens of thousands, hundreds of thousands, millions. The kind of pressure that would crush a deep-sea submersible like a tin can, and then crush the resulting speck of metal into an even smaller speck. As we sink, the temperature paradoxically starts to rise due to this immense compression, from cryogenic cold to thousands of degrees Celsius. It's in this extreme environment, perhaps 7,000 to 8,000 kilometers below the cloud tops, that the magic, or rather the brutal physics, happens. The methane, CH4, molecules are torn apart by the pressure and heat. The carbon atoms, squeezed with unimaginable force, begin to crystallize. Diamonds. But these aren't gentle snowflakes. These are effectively hailstones of pure carbon, perhaps initially small like grains of soot, then growing as they fall, accreting more carbon. Diamond rain sounds delicate. The reality is more like a continuous shower of abrasive, super-hard particles, sinking through a supercritical fluid ocean of water, ammonia, and methane ices. Not ice as we know it, but a hot, dense, electrically conductive fluid state. It's less singing in the rain, and more being sandblasted by gems in hell. And where do these diamonds go? They continue to sink, pulled down by their density, through this bizarre, exotic ocean. Perhaps some theories suggest they eventually form a layer, a vast stratum of solid diamond, miles thick, surrounding the planet's rocky core. Or maybe, if the temperatures and pressures are right, they melt into a liquid diamond ocean. Imagine that, a swirling, molten sea of carbon with diamond icebergs perhaps bobbing on its surface. Utterly alien, utterly spectacular, and utterly terrifyingly lethally inhospitable. The value of these diamonds? In terms of human economics, zero. You can't get to them. You can't mine them. You can't even send a probe to photograph them directly in their native environment. It would be destroyed long before it reached that depth. Their value is purely scientific, a testament to the astonishing behavior of matter under conditions far beyond our everyday experience. They are a beautiful, glittering example of the universe's indifference to life. It creates these wonders, these gemstone showers on a planetary scale, in places where no life as we know it could possibly appreciate them, let alone survive the experience. It's a fascinating juxtaposition, isn't it? The most prized gem on Earth, a symbol of wealth and enduring love, here becomes just another form of precipitation, a geological process on a colossal scale, occurring in an environment that would annihilate you in microseconds. Makes you appreciate that gentle spring shower, doesn't it? The one that just makes your hair a bit damp, rather than flaying you with supersonic diamond shrapnel. Think about the implications. These gas and ice giants, which from afar look like serene, banded orbs or beautiful blue spheres, are actually raging infernos of pressure and exotic chemistry in their depths. Their tranquil exteriors hide hearts of unimaginable violence and bizarre material states. The universe is full of these deceptive appearances. A beautiful nebula might be a lethal radiation bath. A glittering star cluster might be a gravitational minefield. And a planet that rains diamonds is a place you wouldn't want to visit, even with the universe's best umbrella. This is the cosmic buzzkill aspect of our journey, presented with a wry smile. We marvel at the wonder, the sheer audacity of diamond rain. And then we remember, oh yes, that place would also crush us into a subatomic smear while simultaneously boiling and freezing us. It's important to have that perspective. It keeps us humble. It reminds us that the universe is not designed for our comfort or convenience. It simply is in all its beautiful, terrible, diamond-raining glory. So, as you drift away from these hellish, gem-producing worlds, carry with you that image, raining shards on hellish worlds. A beautiful, stark reminder of the raw, untamed power of the cosmos, and the often unbridgeable gulf between imagining a treasure and actually being able to enjoy it. It's enough to make you content with a nice, quiet, terrestrial zircon, isn't it? Or perhaps just a really good night's sleep, dreaming of impossible rains. Leaving behind the glittering, lethal rains of the ice giants, our cosmic journey now takes us to even more extreme frontiers of matter, to places where the very laws of physics are stretched to their breaking point. We're venturing towards the bizarre, almost mythical objects known as neutron stars. These aren't just stars. They are the super-dense remnants of massive stars that have exploded as supernovae. And within their crusts, we find a substance so strange, so incredibly strong, that it makes diamonds look like soft cheese. Prepare to encounter nuclear pasta, the universe's densest and perhaps weirdest deli counter. Imagine a star much more massive than our sun, reaching the end of its life. It has fused elements all the way up to iron in its core, and iron fusion doesn't release energy, it consumes it. The delicate balance between gravity pulling inwards and fusion pushing outwards is broken. Gravity wins. Catastrophically. The core collapses in a fraction of a second, from something perhaps the size of Earth down to a sphere just a few kilometers across. This implosion triggers a shockwave that blasts the star's outer layers into space in a spectacular supernova explosion, one of the most energetic events in the universe. What's left behind is this tiny, incredibly dense ball, a neutron star. How dense? Imagine taking the entire mass of our Sun, 333,000 times the mass of Earth, and crushing it down into a city-sized sphere, perhaps 20 kilometers in diameter. A single teaspoonful of neutron star material would weigh billions of tons on Earth. Billions. If you tried to bring that teaspoonful to Earth, you couldn't, but let's imagine, it would plummet through the planet like a stone through mist, probably settling comfortably in the core, having caused a rather significant amount of localized geological chaos on its way down. Not ideal for your kitchen counter. Now, what is this stuff made of? Under such extreme pressures, atoms themselves can't survive. Electrons are squeezed into protons, forming neutrons. Hence, neutron star. The core is likely a bizarre soup of neutrons, perhaps with some exotic particles mixed in. But it's the crust of the neutron star, the outer kilometer or so, that holds our current culinary curiosity. As you go deeper into the crust, the pressure increases, but not yet enough to completely obliterate atomic nuclei. Instead, these nuclei, remnants of iron and other elements from the original star, are squeezed and distorted in truly extraordinary ways. They get so close together that the strong nuclear force, which usually binds protons and neutrons within a nucleus, and the electromagnetic force, which makes protons repel each other, engage in a complex tug-of-war. The result? The nuclei deform and merge, creating structures that, when modeled by astrophysicists, bear an uncanny resemblance to various forms of pasta. Seriously. At relatively lower pressures in the crust, the nuclei might form spherical clumps, which physicists whimsically call gnocchi. Go a bit deeper, and these gnocchi fuse into long cylinders, resembling spaghetti. Deeper still, the spaghetti strands merge into flat sheets like lasagna. Then, as you approach the core, these structures invert. The lasagna sheets might have cylindrical holes drilled through them, anti-spaghetti, or bucatini perhaps. And eventually, these holes might become spherical bubbles of less dense nuclear matter within a denser medium, anti-gnocchi, or Swiss cheese if you prefer. This entire zoo of bizarre nuclear configurations is collectively, and wonderfully, known as nuclear pasta. This isn't just a cute analogy. These are real, we think, based on strong theoretical models, phases of matter, where protons and neutrons arrange themselves into these complex geometric shapes to minimize their energy under colossal pressure. And this nuclear pasta is thought to be the strongest material in the entire universe. By some estimates, it could be 10 billion times stronger than steel. To break a small piece of nuclear pasta, you'd need to exert more force than to break any other known substance. It's incredibly rigid, incredibly dense. Diamonds are brittle by comparison. So, picture yourself, from a very, very safe distance. Of course, neutron stars are also sources of intense radiation and possess magnetic fields trillions of times stronger than Earth's, which would happily unravel your constituent atoms, peering at the surface of a neutron star. The surface itself is probably a crystalline lattice of iron nuclei. But just a little way beneath that, the real weirdness begins. layers of gnocchi transitioning to spaghetti, then to lasagna, each stratum a different configuration of unimaginably dense matter, all crushed together under gravity so intense it bends light significantly. The universe, it seems, has a rather playful, if somewhat macabre, sense of humor when it comes to naming its most extreme creations. Nuclear pasta. It sounds like something a very ambitious, possibly unhinged cosmic chef might dream up. Tonight's special, neutron star lasagna, served with a side of crushed atoms and a drizzle of pure gravitational despair. The value of nuclear pasta? Again, not something you can mine. Not something you can bring home. Its existence is confined to these ultra-dense stellar corpses. Its value is entirely scientific. Studying nuclear pasta, even theoretically, helps physicists understand the behavior of matter under conditions that are impossible to replicate on Earth. It pushes the boundaries of nuclear physics, teaching us about the fundamental forces that govern the universe. It helps us understand the structure of neutron stars themselves, which are fascinating laboratories for extreme physics. It's a testament to the sheer strangeness the universe can conjure up. We think we understand matter with our familiar solids, liquids, and gases. But out there, in the crucibles of dying stars, matter can twist itself into forms that defy our everyday intuition. Forms that are stronger, denser, and weirder than anything we could have imagined without the guiding light of physics. So, as you drift in the cosmic silence, let the thought of nuclear pasta settle. The universe's densest deli counter, serving up dishes of unimaginable strength, cooked under pressures that boggle the mind. It's a reminder that even in death, stars can give birth to wonders, strange, inaccessible, and utterly fascinating. No need to sample the menu though. Just admire the cosmic cuisine from a very, very safe distance. The indigestion would be, quite literally, astronomical. We've just peeked into the universe's strangest deli, marveling at the theoretical menu of nuclear pasta and gnocchi, spaghetti, lasagna, all cooked up in the unimaginable pressures of a neutron star's crust. It sounds almost whimsical, doesn't it? A cosmic chef with a penchant for extreme cuisine. But let's now take a slightly deeper, more sobering breath and contemplate the sheer, unadulterated horror of the environment that creates these delicacies. Because while nuclear pasta might sound quaint, the conditions required for its existence are anything but. This isn't just about inaccessible treasure. It's about a bite of pure cosmic horror, a taste of an environment so alien and hostile it redefines the word extreme. Imagine trying to get a sample. Let's suspend all known laws of physics and engineering for a moment and pretend you have a spaceship capable of approaching a neutron star. First, the gravity. As we mentioned, a neutron star packs the mass of a sun into a city-sized sphere. The gravitational pull at its surface is about 200 billion times stronger than Earth's. If you were to somehow stand on its surface, you'd be a two-dimensional smear thinner than paint. The force would be so immense that even the slightest imperfection, a mountain no taller than a bacterium, would be flattened instantly. Your spaceship, no matter how robust, would be subject to tidal forces that would rip it apart atom by atom long before you got close. The difference in gravity between the near side and the far side of your ship would be so extreme, it would stretch and shred you in a process charmingly called spaghettification. A rather ironic culinary echo given our topic. But let's say, through some unimaginable cosmic magic, you survive the gravity and the tidal forces. Next up, the magnetic field. Neutron stars can have magnetic fields trillions, even quadrillions of times stronger than Earth's. These aren't your friendly refrigerator magnet fields. These are fields so powerful they would distort the electron clouds of your atoms, effectively destroying the chemistry that makes you, well, you. Your very molecules would cease to exist in any recognizable form. Your ship's electronics would be less than useless. They'd be vaporized streams of charged particles. Even if you were made of pure, non-magnetic neutronium, which you're not, the changing magnetic fields would induce currents that would instantly heat you to millions of degrees. So, not ideal for a comfortable tasting session. Then there's the radiation. Neutron stars, especially young ones called pulsars, are spinning incredibly fast, sometimes hundreds of times per second. Their powerful magnetic fields, misaligned with their spin axis, sweep beams of intense radiation across space, like cosmic lighthouses. If one of those beams were to hit your hypothetical ship, you'd be bathed in a torrent of X-rays, gamma rays, and charged particles that would sterilize, atomize, and generally ruin your entire day and indeed your entire existence in a fraction of a second. It's like trying to take a sample from the heart of an exploding nuclear bomb, while simultaneously being inside a particle accelerator and a giant microwave oven. And let's not forget the temperature. While the surface of a neutron star might be a cool 1,000,000 degrees Celsius, which is already hot enough to vaporize any known material, the interior where the nuclear pasta is formed is even hotter, reaching perhaps hundreds of millions of degrees. This isn't the kind of heat you can shield against with a few ceramic tiles. This is heat that would turn any conceivable sampling probe into an expanding cloud of plasma. So, this nuclear pasta, this strongest material in the universe, is forged in an environment that is, by any human standard, a literal hell. A place of crushing gravity, atom-shredding magnetic fields, lethal radiation, and unimaginable temperatures. The universe isn't just cooking pasta here. It's operating a blast furnace of cosmic proportions, where the ingredients are fundamental particles and the forces are the universe's most brutal. The very idea of collecting, it is so far beyond our capabilities that it borders on the absurd. It's not just difficult, it's fundamentally impossible given our current understanding of physics and material science. Nuclear pasta will likely forever remain a theoretical delicacy, something we can model on supercomputers, something that tantalizes our understanding of extreme matter, but something we can never, ever touch or taste. And perhaps that's for the best. Some cosmic dishes are best left on the menu, unsampled. The horror of its birthplace serves as a stark reminder of the sheer, raw, untamed power of the cosmos. We, with our fragile biological forms and our delicate technologies, are adapted to a tiny, gentle sliver of reality on the surface of a small, calm planet. Out there, in the hearts of dead stars, the universe operates on a scale of violence and extremity that we can barely comprehend, let alone survive. This isn't meant to induce anxiety, but rather a profound sense of awe, tinged with a healthy dose of existential respect. The universe is capable of creating things of incredible strength and bizarre beauty, but it often does so in ways that are utterly indifferent to and completely incompatible with life as we know it. The conditions that forge nuclear pasta are not just inhospitable, they are annihilating. So, as you drift in the quiet of your mind, let this image settle. The strongest food in the universe, cooked in the most terrifying kitchen imaginable. It's a humbling thought. It puts our terrestrial concerns, our daily struggles with burnt toast or lumpy gravy, into a rather grand perspective. At least our kitchens don't have magnetic fields that can rewrite our atomic structure. Small mercies, eh? The universe's menu is vast and varied, and some of its offerings are best appreciated from a very, very, very great distance. Nuclear pasta is one such dish. A terrifying testament to the creative and destructive power simmering in the cosmic cauldron. Sweet dreams of slightly less extreme culinary adventures. Having wisely decided to give the neutron star deli a wide berth, let our cosmic current carry us towards a different kind of extreme, not of density and pressure, but of sheer, audacious elemental ambition. We're venturing into the realm of the alchemist's ultimate dream, a place that may only exist in the fertile landscape of theoretical physics and the hopeful hearts of nuclear scientists. We are searching for the island of stability, home to undiscovered, super-heavy elements, materials with properties so extraordinary they might rewrite technology, or perhaps just our understanding of matter itself. This is the alchemist's final fantasy, played out on a nuclear scale. You might remember the periodic table from your school days, that neat chart of elements from lightweight hydrogen and helium, through familiar faces like carbon, oxygen, iron, and gold, all the way up to the heavyweights like uranium and plutonium. Each element is defined by the number of protons in its nucleus. As you add more protons, the element generally becomes heavier and, beyond a certain point, much less stable. Most elements heavier than lead, which has 82 protons, are radioactive, meaning their nuclei spontaneously decay, transforming into lighter elements and releasing energy. For the very heaviest elements we've managed to create in laboratories, fleeting things with names like oganesson, element 118, their existence is measured in milliseconds or even microseconds before they disintegrate. They are phantoms, briefly conjured into being by smashing lighter nuclei together at incredible speeds. This increasing instability makes it seem like there's a natural limit to how heavy an element can be. The electromagnetic repulsion between all those positively charged protons in a dense nucleus becomes overwhelming, tearing it apart. It's like trying to hold together an ever larger bag of angry, mutually repellent cats. Eventually the bag breaks. However, nuclear physics is a wonderfully complex beast. There are certain magic numbers of protons and neutrons that can make a nucleus unusually stable, due to the way these particles arrange themselves in shells, similar to how electrons arrange themselves in shells around an atom. Think of it like finding a particularly well-balanced configuration for your bag of angry cats, where they somehow, against all odds, achieve a moment of grumpy zen. This is where the island of stability comes in. Theoretical physicists predict that beyond the currently known superheavy elements, there might be a region, an island, in a sea of instability, where new combinations of protons and neutrons could lead to elements that are significantly more stable. We're not talking about elements that last forever, perhaps, but elements that might have half-lives of minutes, hours, days, or even, in the wildest dreams of physicists, thousands or millions of years. These would be truly new forms of matter, with potentially extraordinary and completely unknown properties. Imagine it, an element with, say, 114, 120, or even 126 protons, nestled comfortably in the center of this predicted island. What would it be like? Would it be a superdense metal? A strange semiconductor? Would it possess bizarre magnetic or optical properties? Could it be a room temperature superconductor? Or perhaps, more fantastically, could it be a source of incredibly compact energy, or even have applications in medicine or materials science that we can't yet dream of? The quest for the island of stability is one of the great frontiers of modern nuclear science. Laboratories around the world, with their giant particle accelerators, are painstakingly trying to create these elusive elements, one atom at a time. They do this by firing beams of one type of atomic nucleus at a target made of another heavy element, hoping that, very occasionally, two nuclei will fuse to form a new, even heavier nucleus. It's an incredibly difficult process, like trying to get two microscopic hyperfast billiard balls to stick together perfectly after a head-on collision, and then hoping that the resulting slightly larger ball doesn't immediately fall apart. The odds are astronomically low. For every successful fusion event that creates a superheavy atom, trillions upon trillions of projectile nuclei might just bounce off or shatter the target. If we could create even a few atoms of an element from the island of stability, and if those atoms lasted long enough to study, the scientific value would be immense. It would confirm our theories about nuclear structure, provide insights into the limits of matter, and potentially open up entirely new avenues of research. And if, by some incredible stroke of luck, one of these elements turned out to have practical applications, well, the impact could be revolutionary. Think of the alchemists of old, toiling away in their dusty laboratories, trying to turn lead into gold. They were driven by a dream of transmutation, of creating something precious from something common. Modern nuclear physicists are, in a way, their intellectual descendants. They are not trying to create gold, we can already do that, though it's far too expensive to be practical, but they are trying to create entirely new forms of matter, elements never before seen on Earth, perhaps never before seen in the universe, except maybe fleetingly in the heart of supernovae or neutron star mergers, nature's own violent particle accelerators. This is a treasure hunt not for existing riches, but for riches yet to be born, for potential locked away in the very heart of the atom. It's a search driven by pure curiosity, by the desire to understand the fundamental rules of the cosmic game, and perhaps, just perhaps, to find a new piece on the board with game-changing properties. So, as you drift in the peaceful dark, imagine these scientists, modern-day alchemists, patiently sifting through the subatomic realm, hoping for a glimpse of that fabled island. An island not of sand and palm trees, but of surprisingly stable, super-heavy nuclei. It's a place of immense theoretical beauty, a testament to the subtle and often counterintuitive laws that govern the building blocks of everything. The alchemist's final fantasy, not of gold, but of knowledge and the quiet, thrilling possibility of discovering something utterly new under, or rather beyond, the sun. We've been dreaming of the alchemist's final fantasy, haven't we? That island of stability, a mythical land populated by super-heavy elements with potentially wondrous properties, just waiting to be discovered by patient scientists with very large, very expensive machines. It's a beautiful, noble quest, this pursuit of new matter. But as with all our cosmic treasure hunts so far, there's a rather large and often deflating price tag attached. And it's not just a monetary one. The cost of reaching this island, of conjuring even a single fleeting atom of these mythical elements, is a stark reminder of the universe's resistance to yielding its deepest secrets. Imagine the scene, a vast, circular tunnel, kilometers in circumference, housing a particle accelerator. Inside, beams of ions, atoms stripped of some of their electrons, are whipped up to incredible speeds, approaching a fraction of the speed of light, guided by powerful superconducting magnets cooled to near absolute zero. This isn't your average laboratory setup. This is a scientific instrument on the scale of a small city, consuming megawatts of power, operated by teams of hundreds of physicists, engineers, and technicians. The cost to build and run such a facility? Billions of dollars. Or euros. Or yen. Pick your favorite large currency. The numbers are universally eye-watering. And what is all this monumental effort for? To take a beam of, say, calcium-48 ions, a relatively neutron-rich isotope of calcium, and smash it into a target made of, perhaps, americium-243, a heavy radioactive element. For weeks, months even, this beam pummels the target. Trillions upon trillions of calcium ions per second. And the vast, overwhelming majority of these collisions achieve nothing. The ions bounce off. They shatter the target nuclei into smaller fragments. They might fuse briefly and then immediately fly apart. It's an exercise in extreme patience and statistical probability. Then, once in a blue moon, or more accurately, once in many, many trillions of collisions, a calcium nucleus and an americium nucleus might fuse just right. Their protons and neutrons momentarily overcome their mutual repulsion and the disruptive forces, merging to form a new super-heavy nucleus. For a fleeting instant, an atom of element 115, Moscovium as it happens, which has been created this way, might exist. But exist is a strong word. The half-life of Moscovium isotopes is measured in milliseconds. That means if you create one atom, there's a 50% chance it will have decayed into something else before you can even say, Eureka. To detect it, scientists use incredibly sophisticated arrays of detectors that can identify the characteristic signature of its decay products. The alpha particles or fission fragments it emits as it disintegrates. They're not seeing the atom itself. They're seeing its ghost, its rapidly fading footprint. And for elements predicted to be on the true island of stability, perhaps with even more protons, the production rates are expected to be even lower. Maybe one atom per week of continuous bombardment. Maybe one atom per month. Or even less. We are talking about the ultimate needle in a haystack search, where the haystack is the size of a solar system and the needle is a single, invisible, and very short-lived atom. The sheer expenditure of energy, resources, and human intellect to create and detect these ephemeral specks of new matter is almost comical in its disproportion. It's like building a pyramid to find a single, unique grain of sand. And yet, the drive to do so is profound. It's about pushing the boundaries of knowledge, about testing the limits of our understanding of the universe. Each successful atom, however fleeting, is a tiny victory, a confirmation that our theories about nuclear structure are, at least in part, on the right track. But let's consider the value of these elusive atoms. Scientifically, as we've said, it's immense. But practically, if an element has a half-life of milliseconds or even minutes, its applications are going to be severely limited. You can't build a super strong bridge or a revolutionary new computer out of something that vanishes before you've finished your coffee. Even if we found an element on the island of stability with a half-life of years, the production rate of 1 atom per month, if we're lucky, means accumulating enough of it to do anything useful would take, well, longer than the age of the universe probably. The existential cost isn't just financial. It's the sheer, almost heroic effort expended for such an intangible, fleeting reward. It makes you ponder the nature of scientific pursuit. Is it worth it? Most scientists involved would give a resounding yes. Because it's not just about the atom itself. It's about the journey, the technology developed along the way, the deeper understanding gained, the confirmation or refutation of fundamental theories. But from our sleepy cosmic perspective, there's a certain wry amusement to be found. Humanity, in its relentless curiosity, building these colossal machines, these modern-day cathedrals of science, all to glimpse a form of matter that exists for less time than it takes to blink. It's a testament to our ambition, certainly, and perhaps also to our endearing, slightly absurd, obsession with the unknown. The island of stability remains, for now, largely a theoretical paradise. We've perhaps touched its shores with elements like flerovium-114 or livermorium-116, which show slightly increased stability compared to their neighbors, but we're likely still in the shallow coastal waters, not the heart of the island where truly long-lived superheavies might reside. So, as you drift, imagine these fleeting superheavy atoms, born of incredible violence, existing for a cosmic nanosecond and then vanishing like a sigh. Their creation is a triumph of human ingenuity, a testament to our desire to explore the very edges of material existence. But their fleeting nature and the astronomical expense of their birth also serve as a humbling reminder. The universe holds its treasures tightly, and sometimes the price of a glimpse is almost everything we have. It makes you wonder, doesn't it, what other impossibly expensive, wonderfully transient truths are still out there, waiting for us to build an even bigger machine to chase them. We've journeyed from the dusty plains of the moon to the glittering rain of gas giants, from the bizarre pasta of neutron stars to the fleeting phantoms of superheavy elements. Each treasure has come with its own unique set of cosmic caveats, its own brand of beautiful impracticality or terrifying inaccessibility. But now, my sleepy voyagers, we approach the pinnacle of cosmic expense, the undisputed champion of things you can't afford. We are drifting towards the realm of antimatter, the trillion-dollar teardrop, a substance so potent, so difficult to create and contain, that it makes everything else we've discussed look like loose change found down the back of the cosmic sofa. What is antimatter? In essence, it's a mirror image of ordinary matter. For every particle of matter, like an electron or a proton, there's a corresponding antiparticle with the same mass but opposite charge, and some other quantum properties flipped. So, an anti-electron, also known as a positron, has the same tiny mass as an electron but a positive charge. An antiproton has the same mass as a proton but a negative charge. These aren't just theoretical constructs. Antiparticles are very real. Positrons are routinely used in medical imaging, PET scans, positron emission tomography. Antiprotons can be created in particle accelerators. When a particle of matter meets its corresponding antiparticle, they don't just bump into each other. They annihilate. Poof. gone. In a flash of pure energy, typically in the form of gamma rays. And not just a little bit of energy. According to Einstein's famous equation, E equals mc squared, the amount of energy released is equivalent to the total mass of the annihilating particles multiplied by the speed of light squared. The speed of light squared is a very, very, very big number. This means that matter-antimatter annihilation is the most efficient energy release process known to science. It converts 100% of the mass into energy. By comparison, nuclear fission, like in a nuclear power plant, converts about 0.1% of mass into energy. Nuclear fusion, like in the sun or a hydrogen bomb, converts about 0.7%. Antimatter is orders of magnitude more potent. A single gram of antimatter annihilating with a gram of matter would release roughly the same amount of energy as the atomic bomb dropped on Hiroshima, about 43 kilotons of TNT equivalent. A teardrop-sized amount, say a milligram, 1,000th of a gram, would still pack a punch equivalent to about 43 tons of TNT, enough to make a very significant crater. This incredible energy density is why antimatter is the darling of science fiction writers dreaming of Starship fuels or unimaginably powerful weapons. So, if it's so powerful, why aren't we all zipping around in antimatter-powered flying cars? Therein lies the rub. The universe, it seems, has a strong preference for regular matter. When the Big Bang occurred, it should have produced equal amounts of matter and antimatter. And if it had, they would have all annihilated each other very early on, leaving behind a universe filled with nothing but radiation, and certainly no galaxies, stars, planets, or us. Which would have made for a very short and rather dull bedtime story. But for some reason, still one of the biggest mysteries in physics, known as baryon asymmetry, there was a slight imbalance. For roughly every billion pairs of matter and antimatter particles, there was one extra matter particle. All the pairs annihilated, leaving behind the radiation that forms the cosmic microwave background, and that 1 in a billion leftover bit of matter went on to form everything we see around us. The universe, it seems, performed a cosmic sleight of hand and hid almost all the antimatter. Or perhaps it was never there in quite the same quantity. We just don't know. The result is that naturally occurring antimatter is exceedingly rare in our matter-dominated universe. We see fleeting antiparticles produced in high-energy events like cosmic ray collisions or radioactive decay, but no antimatter asteroids, no anti-stars, no anti-galaxies. As far as we can tell, an anti-galaxy would look identical to a normal one until it met a normal one, at which point there would be a rather noticeable kerfuffle. This means if you want antimatter, you have to make it. And making it is extraordinarily difficult and inefficient. The main place we do this is at particle accelerator facilities like CERN. They smash beams of protons into targets. Most of the debris is ordinary matter, but very occasionally, if the collision is energetic enough, some of that energy can be converted into a particle-antiparticle pair, say a proton and an antiproton or an electron and a positron. It's E equals mc squared running in reverse, energy turning into mass. But the yields are pitiful. To create one antiproton, you might need 1 million or even 1 billion proton collisions. It's like trying to make a specific type of sand grain by smashing 2 boulders together repeatedly. Most of what you get is just dust and rubble. And then once you've made your precious few antiparticles, you have to catch them and store them. You can't just put them in a bottle because the moment an antiparticle touches the ordinary matter walls of the bottle, poof. Annihilation. So, scientists use sophisticated electromagnetic traps, penning traps, which use carefully shaped electric and magnetic fields to hold charged antiparticles suspended in a vacuum, preventing them from touching anything. These traps are complex, energy-intensive, and can only hold a very small number of antiparticles at a time. CERN has managed to trap antihydrogen atoms, an antiproton orbited by a positron, for several minutes, which is a monumental achievement, but we're talking about a few thousand atoms at most. Now the cost. Well, the cost. Because of the incredible energy required and the minuscule yields, The price of producing antimatter is, well, astronomical doesn't even begin to cover it. Estimates vary, but figures in the realm of tens of trillions of US dollars per gram are often quoted. Some estimates go even higher to quadrillions. That's a 1 with 15 zeros after it. Per gram. To put that in perspective, the entire world's GDP is somewhere around $100 trillion. So, a gram of antimatter would cost more than the annual economic output of our entire planet. This makes antimatter, by a staggering margin, the most expensive substance ever conceived or created by humanity. That tiny teardrop-sized amount we mentioned, the milligram that could level a city block, that would cost you tens of billions of dollars at least. Suddenly, those lunar helium-3 mining operations look like a bargain basement deal. So, as you drift in this serene darkness, contemplate this trillion-dollar teardrop. A substance that holds the promise of ultimate energy, the key to star travel in our dreams, yet is so mind-bogglingly expensive to produce that it remains firmly in the realm of the almost purely theoretical for any large-scale application. It's the universe dangling the ultimate carrot, then putting it on a stick so long and so pricey that we can only gaze at it with a mixture of awe and profound budgetary despair. The ultimate treasure, guarded by the ultimate price tag. We've just been introduced to antimatter, the universe's most expensive bauble, a substance whose price tag makes planetary GDPs look like pocket money. We know it's made of antiparticles, mirror images of the stuff that makes up you, me, and this rather comfortable, hopefully, bed you're drifting in. And we know that when matter meets antimatter, they embrace in a final, spectacular act of mutual annihilation, converting their entire mass into pure, incandescent energy. It's a destructive beauty, a fundamental process of uncreation that paradoxically hints at the very creation of the universe itself. Let's linger for a moment on that annihilation. It's not just an explosion in the conventional sense like TNT or even a nuclear bomb, where atoms are merely rearranged or split. This is more profound. This is matter returning to a more fundamental state, often high-energy photons, particles of light, gamma rays. Imagine a positron, that anti-electron with its positive charge drifting through space. It encounters an ordinary electron with its negative charge. They are drawn to each other by their opposite charges. For a fleeting moment, they might even orbit each other, forming a brief, exotic atom called positronium, a highly unstable entity doomed from its inception. Then, in a timescale far shorter than a blink, they touch. And in that instant they both cease to exist as particles with mass. Their properties, charge, spin, lepton number, all cancel out perfectly. All that remains is energy, bursting forth as 2, or sometimes 3, gamma-ray photons, streaking away at the speed of light in opposite directions to conserve momentum. It's a perfectly clean conversion. No leftover bits, no messy byproducts, just pure energy. The universe balancing its books with ruthless efficiency. It's a beautiful symmetry in a stark, fundamental way. Creation and annihilation, two sides of the same cosmic coin. The energy released is immense, as we've discussed, making antimatter a theoretically perfect fuel. But it's also a reminder of the universe's capacity for total erasure. If you were made of antimatter, and you shook hands with an ordinary matter person, there wouldn't be a handshake. There would be a flash of light, a burst of radiation, and two rapidly expanding clouds of superheated gas where two individuals used to be. Not exactly conducive to interstellar diplomacy. This brings us back to that profound cosmic mystery. Where is all the antimatter? The standard model of particle physics, our best current theory of fundamental particles and forces, predicts that the Big Bang should have created matter and antimatter in virtually equal amounts. If so, they should have annihilated each other completely in the very early universe, leaving behind a cosmos filled only with photons, a diffuse glow of radiation, and nothing else. No stars, no galaxies, no planets, no life. Certainly, no one to lie in bed and contemplate the philosophical implications of their own non-existence. The fact that we are here, that the universe is filled with lumpy bits of matter like us, means that this perfect symmetry must have been broken ever so slightly. For every billion antiprotons, there must have been 1,000,000,001 protons. That tiny fractional excess, that 1 in a billion left over, is what constitutes the entire material universe we observe. It's a staggering thought. We are the cosmic leftovers, the rounding error in the universe's matter-antimatter budget. Makes you feel special, doesn't it? Or perhaps just incredibly statistically improbable. Scientists are desperately searching for the reason behind this asymmetry. Is there some subtle difference in the way matter and antimatter particles decay or interact with fundamental forces that gave matter a slight edge? Experiments at places like CERN are meticulously comparing protons with antiprotons, looking for any tiny discrepancy in their mass, charge, or magnetic moment that could explain this cosmic imbalance. So far, they appear to be perfectly symmetrical, which only deepens the mystery. What process in those first fiery moments of creation tipped the scales in favor of matter? It's one of the biggest unanswered questions in all of physics, the baryon asymmetry problem. Imagine the universe as a vast, silent courtroom. Matter stands accused of existing while its twin, antimatter, is conspicuously absent, presumed annihilated. The evidence? The motive? Unknown. The universe, as usual, isn't talking, just presenting us with the fait accompli of a matter-dominated reality. The implications are profound. If we could understand why matter won, it might unlock new physics beyond the standard model. It might even give us clues about the very earliest moments of the Big Bang, or the nature of fundamental forces we haven't yet discovered. And what if there are vast regions of antimatter out there? Distant anti-galaxies in some far-flung corner of the cosmos, separated from our matter-dominated neighborhood by unimaginable voids? If an anti-galaxy were to collide with a normal galaxy, the resulting annihilation event would be the most spectacular firework display in the universe, releasing energy on a scale that dwarfs even quasars. Astronomers have looked for the characteristic gamma-ray signatures of such large-scale annihilations at the boundaries of galaxy clusters, but so far, nothing definitive has been found. It seems our local universe, at least, is reassuringly, or perhaps disappointingly, made of the same stuff we are. So, as you drift deeper into relaxation, ponder this cosmic imbalance. The annihilation of matter and antimatter is a process of stark, beautiful, and terrifying efficiency. And our very existence is a testament to a flaw, a tiny imperfection, in that otherwise perfect symmetry. We are the children of a broken cosmic mirror. It's a thought that can be both humbling and strangely comforting. Humbling because it underscores our contingency, our status as a cosmic afterthought. Comforting, perhaps, because imperfections, it seems, are necessary for existence. A universe of perfect symmetry would have been a universe empty of us. So, let's raise a sleepy toast to asymmetry, to the 1 in a billion chance that allowed matter to prevail, allowing you to be here now, gently drifting on the verge of dreams, in a universe that still holds its deepest secrets with a tantalizing, silent smile. We've marveled at the sheer destructive beauty of antimatter annihilation, pondered its mysterious absence from our universe, and shuddered slightly at its multi-trillion-dollar per gram price tag. But humanity, bless our optimistic and often foolhardy hearts, rarely lets a little thing like impossibly expensive, or could accidentally vaporize a continent, get in the way of a good dream. And the dream associated with antimatter is a very big one indeed. Starships. Fast starships. The kind that could actually get us to another star system within a human lifetime. For interstellar travel, conventional chemical rockets like the ones that took us to the moon are pathetically inadequate. They just don't provide enough oomph, enough specific impulse, a measure of rocket efficiency. Even the most advanced theoretical propulsion systems like nuclear fusion rockets, using that Helium-3 we talked about, perhaps, while vastly better, would still mean journeys of decades, centuries, or even millennia to the nearest stars. Alpha Centauri, our closest stellar neighbor, is over 4 light-years away. That's about 40 trillion kilometers. Your frequent flyer miles would be legendary, but you'd likely be a rather dusty skeleton upon arrival. Antimatter, however, changes the equation. Because matter-antimatter annihilation converts 100% of mass into energy, it offers the highest possible specific impulse. In theory, an antimatter-powered rocket could accelerate a ship to a significant fraction of the speed of light, say 10%, 20%, or in the wildest sci-fi dreams, even higher. At those speeds, a trip to Alpha Centauri could be reduced to decades, or even years from the perspective of the travelers, thanks to time dilation, another of Einstein's little gifts. Imagine a sleek starship, its engines glowing with the contained fury of annihilating particles. Not by burning fuel, but by carefully, precisely feeding tiny amounts of antimatter and matter together in a reaction chamber. The resulting blast of gamma rays, or perhaps charged particles, if the annihilation is designed to produce them like pion rockets, is then directed by powerful magnetic nozzles to produce thrust. It's the ultimate rocket engine. The amounts of antimatter required are surprisingly small, thanks to its incredible energy density. A few tens of milligrams might be enough for a flyby mission to Alpha Centauri. A few kilograms might be sufficient for a more ambitious round trip with deceleration and exploration. Sounds almost manageable, doesn't it? Until you remember that even a milligram costs more than the annual budget of most countries. So, fueling your starship becomes less of an engineering problem and more of a how do we acquire several planets worth of GDP problem. A budgetary black hole indeed. Let's put this in perspective. If we take the optimistic and probably wildly unrealistic future price of, say, $10 billion per milligram of antimatter, a massive discount from current estimates, then a mission needing, say, 100 milligrams of antimatter for fuel would cost a cool $1 trillion. Just for the fuel. That doesn't include the cost of the Starship itself, the research and development, the crew training, assuming it's manned, the life support, the therapy sessions for the accountants who have to approve the budget. You get the idea. It's the kind of expenditure that makes governments nervous and taxpayers reach for their pitchforks. And then there's the not insignificant problem of safety. You're carrying a substance on your ship that, if its containment field were to fail, would annihilate with the ship itself, releasing the energy of multiple nuclear bombs. Houston, we have a problem, would be a rather dramatic understatement. The engineering challenges of creating a foolproof magnetic storage system for antimatter, one that can withstand the stresses of acceleration, potential micrometeoroid impacts, or just a clumsy engineer tripping over a power cord, are formidable. One tiny flicker in the containment, and your $1 trillion starship becomes a rapidly expanding cloud of very expensive, very radioactive vapor. Not the glorious arrival at a new star system you were hoping for. So, we have this beautiful dream, starship fuel, the key to unlocking the galaxy. And then we have the comically absurd, terrifyingly stark reality. The cost is so high it's almost a philosophical concept rather than a practical number, and the risks are so enormous that any sane risk assessment algorithm would probably just shut itself down in protest. It's a classic case of the universe offering an incredible gift, but wrapping it in layers of near impossibility. Here, says the cosmos, is the secret to the stars. All you need to do is figure out how to make quintillions of dollars, invent flawless magnetic bottles, and not blow yourselves up in the process. Good luck with that. The universe can be a real wise guy sometimes. This juxtaposition of the dream and the reality is, in its own way, rather relaxing, isn't it? It puts our own daily financial woes into perspective. Fretting about the gas bill? At least you're not trying to budget for fuel that costs more than all the money in the world. Worried about your car breaking down? At least it won't vaporize a small country if the spark plugs fail. Antimatter, the starship fuel of our dreams, remains for now firmly in the realm of dreams, or at best very, very long-term theoretical possibilities. The leap from creating a few thousand anti-hydrogen atoms in a laboratory trap to fueling a starship is like leaping from paddling a paper boat in a bathtub to commanding an aircraft carrier across the Pacific. It's a leap of many, many orders of magnitude in cost, complexity, and sheer audacity. So, as you drift, let the dream of antimatter starships shimmer in your mind, a beautiful, distant beacon. But let the wry smile accompany it, acknowledging the cosmic joke of its current impracticality. The stars may beckon, but the price of the ticket for now is just a little too steep. Perhaps it's the universe's way of telling us to sort out our own planetary backyard before we go gallivanting off, armed with something that could accidentally erase our celestial neighbors. A sobering yet strangely calming thought as we prepare for the final leg of our sleepy treasure hunt. And so, our grand cosmic treasure hunt draws to a gentle close. We've journeyed from the moon's dusty promise of Helium-3 through the glittering asteroid fields, past raining diamonds on hellish worlds, and dared to peek into the neutron star's bizarre deli counter. We chased the alchemist's dream of super-heavy elements and finally gazed upon the trillion-dollar teardrop of antimatter, the ultimate fuel for futures we can barely imagine. We've whispered of riches beyond comprehension, of materials with powers that defy belief, and of costs that make planetary economies look like piggy banks. What have we found on this sleepy odyssey? Did we fill our celestial pockets with unimaginable wealth? Not quite. In fact, if anything, we've discovered that the universe's most valuable treasures are often the most inaccessible, the most dangerous, or the most comically impractical to acquire. The universe, it seems, isn't particularly interested in our human notions of currency or ownership. Its treasures are often locked away behind barriers of extreme physics, vast distances, or simply eye-watering, soul-crushing expense. The Helium-3 on the moon? A clean energy dream, certainly, but one that requires a mining operation of such monumental scale and cost that it remains, for now, a distant prospect. The platinum and asteroids? Abundant, perhaps, but guarded by the perils of space travel, the complexities of remote mining, and the ironic threat of crashing the very market you seek to supply. Diamonds from chaos? Beautiful, yes, whether star-sized or raining down in crushing atmospheres, but utterly beyond our grasp, silent testaments to cosmic power rather than wearable bling. Nuclear pasta? The strongest stuff in the universe, but cooked in a gravitational and radioactive hell that makes it the ultimate untouchable delicacy. Superheavy elements? Fleeting phantoms, conjured at enormous expense, existing for mere moments, teasing us with glimpses of new physics before vanishing like a subatomic sigh. And antimatter, the most valuable of them all? The key to starships, perhaps, but so mind-bogglingly expensive to produce and so terrifyingly potent to handle that it feels more like a cosmic practical joke than a readily available resource. It's as if the universe is saying, "You want the ultimate power? Fine. But first, you'll need to invent an entirely new global economy, rewrite the laws of risk assessment, and probably develop a very good insurance policy against accidental planetary annihilation." So, if these treasures are largely out of reach, what is the true value we take away from this journey? Perhaps it's not in the material itself, but in the contemplation. In the sheer mind-expanding wonder of what the universe can create. In the humbling realization of our own smallness, our own fragility, set against such cosmic grandeur and extremity. There's a strange comfort in that, isn't there? Our daily anxieties, our terrestrial squabbles, they seem to shrink, to become almost insignificant, when viewed against the backdrop of raining diamonds or trillion-dollar antimatter. The true treasure, perhaps, is the perspective. The universe doesn't hoard its wonders maliciously. It simply operates by its own rules, its own majestic, indifferent, and often terrifyingly beautiful logic. And in trying to understand those rules, in daring to dream of reaching those treasures, we learn more about the universe and ultimately more about ourselves, our ingenuity, our ambition, our capacity for wonder, and yes, even our charming, persistent, and sometimes rather absurd human folly. We set out to find trillion-dollar treasures, and what we found was a universe infinitely richer and more complex than any mere monetary value could ever capture. We found beauty in the bizarre, strength in the extreme, and a profound sense of awe in the face of forces that could unmake us in an instant. And yet, here we are, tiny beings on a small blue planet, capable of contemplating these things, of weaving stories about them, of dreaming of them as we drift off to sleep. That, in itself, is a kind of treasure, isn't it? The capacity for imagination, for curiosity, for reaching out with our minds into the vast, silent, starlit dark. So, as you let go, as you allow the gentle currents of sleep to finally pull you under, remember this cosmic treasure hunt. Remember the glittering, lethal, and impossibly expensive wonders we've explored. And perhaps, realize that the most valuable thing you possess right now is this moment of peace, this quiet sanctuary of your mind, this empty, starlit pocket of consciousness where you can safely ponder the universe's grand, indifferent, and utterly magnificent show. The universe doesn't need your currency, but it offers its wonders freely to the curious mind. And sometimes the most profound riches are not those we can hold, but those that hold us in awe and in peaceful contemplation as we drift towards dreams. And so the cosmic vault gently closes for tonight. The trillion-dollar treasures, the impossible elements, the annihilating energies, they all recede, fading into the soft velvet of the cosmic backdrop. Let them go. They were never really ours to possess, only to ponder, to marvel at, and perhaps to smile wryly at their magnificent, terrifying impracticality. What remains is the quiet hum of the universe, the gentle turning of galaxies, the silent dance of starlight across unimaginable distances. And you, dear Voyager, are a part of that dance, a tiny, precious speck of stardust that learned to think, to feel, to dream. The universe, in all its vast indifference, its capacity for casual obliteration, its penchant for cooking up things that would vaporize you before you could say, ouch, is also the source of your being. A rather amusing paradox, isn't it? It built you and it could unbuild you with a careless shrug. But tonight, in this safe haven, none of that matters. The cosmic radiation is far away. The black holes are keeping their distance. The antimatter is safely unmade. Here there is only the gentle rhythm of your breath, the softening of your thoughts, the slow, inevitable pull towards the deep, restorative ocean of sleep. The universe may be a chaotic, often brutal, and hilariously expensive place if you're trying to mine its secrets. But it's also the grandest show imaginable, and you have a front row seat every single night in the theater of your mind. So let the stardust settle. Let the existential questions hang, unanswered and unimportant for now. Let the quiet of the void be a blanket, and the distant glimmer of stars be a lullaby. You are safe. You are drifting. You are ready for sleep. Sweet dreams, cosmic treasure. You'll need them for whatever fresh absurdities the morrow may bring. Sleep now. Sleep deep.